Now, here's a pretty interesting topic that's really a tree thing. We know that there is a maximum observed height for trees. It's probably around 130 meters to 140 meters, you know, pushing 400 feet. Uh, historic, right now, the tallest measured tree is less than 400 feet in height, but we know historically there likely were a little bit taller trees in existence, but not much taller than the redwoods that we observe now. At any rate, there's some maximum height. And a question has always been, is there some biological explanation for that maximum height in trees? And probably the best candidate for a biological limitation on height is hydraulics. More specifically, limitations to gas exchange in the upper canopy caused by reduced water potential from that drawing water to that great height. Um, so one of the fun things about looking at the literature in this area is you get to see literature from really tall trees. I think you've seen this data set before. This is pre-dawn water potential in tall Douglas fir trees. And this was measured um, from the Wind River canopy crane here. It's a construction crane in an old growth Douglas fir western hemlock forest in Washington state. And they went up some really tall Douglas fir trees, about 60 meters in height. So only 190 feet tall, um, and measured their pre-dawn water potential. And what you can see is that when the soil is at about minus 0.3 megapascals, the foliage at the top of tall trees is at about minus 1 megapascals. It's not transpiring, this is pre-dawn, but just by virtue of the gravitational potential, the leaves at the top of that tree are always at more negative water potential than the soil by quite a bit. And what that means is that the foliage at the top of tall trees is essentially perpetually under water stress, is one way to think about it. Foliage at the top of tall trees, because it has to overcome that gravitational potential, always has relatively negative water potentials and is essentially operating under perpetual water stress. Um, so one of the people that looked at this in great detail was Barbara Bond. Um, in the late 90s, early 2000s, she was a researcher at Oregon State University. And these are some data from ponderosa pine. And she was looking at net photosynthesis rate under a bunch of different environmental conditions. And she plotted net photosynthesis rate of ponderosa pine from these triangles are, shorter, younger trees and taller, older trees. So those data showed that at any particular vapor pressure deficit, for instance, the taller, older trees had lower photosynthesis rates than the shorter, younger trees. And these were all on the same site. So this is not the site where they did the research, but this is a ponderosa pine site. You can see it's a relatively open savanna-like canopy with a mixture of tree sizes. And in the forest they were measuring as an uneven age stance. They had young, short trees and tall, old trees growing in the same environment. So it was a nice situation for comparing that. And hypothesis was that these taller old trees not only were taller, so there's greater gravitational limitations, but they were also more complex. They had longer, twisty branches, and that provided more resistance, more hydraulic resistance, so that the foliage on those taller trees basically always was operating at more negative water potentials. That means the stomata were a little bit more closed, and photosynthesis rates were lower. Well, if you want data from tall trees, redwood is a place to go. Redwoods are the tallest trees in the world, and getting data from them will give you data from really tall trees. So these data, you can see they retrieved leaves or measured leaves as high as neighborhood of 110 feet. I'm sorry, 110 meters above ground, close to 350 feet. There are not any canopy cranes, like I showed you in the other picture, in redwood, so they climbed these trees. They used, shot monofilament line over branches and then pulled climbing ropes up into the crowns of these trees and then used ascenders and rock climbing techniques to climb up into the tops of these trees and do physiological measurements up there. So this stuff is not for the faint of heart. But this is a great set of data showing variation in different physiological parameters associated with height. So what we see here, all of these are related to height above ground. And you can see, their lowest branches are the neighborhood of 40 meters up in the air. So these are, again, tall trees. So what you can see is that water potential. I suspect this is pre-dawn and midday water potential became more negative with height. That as they went above ground, the leaf mass per unit area became larger. That means the leaves became thicker, and I'll show you some pictures in a minute. This is an interesting one. Leaf delta 13C became less negative as they went up in height. And what that means is that there was increasing stomatal closure as you went up in height. Okay, seeing a trend here. And again, as you go up in height, maximum leaf net photosynthesis declined. So some pretty significant changes in physiology and morphology in the case of here associated with height. Likely all related to these declines in leaf water potential and stomatal closure causing reduced net photosynthesis rates. One interesting thing to note is what happens if we take this line for net photosynthesis and extend it downward, okay, to where photosynthesis is zero. That hits zero at about 120 meters. Okay, that tells us that maybe that's a simple extrapolation that maybe sort of the point at which you get zero net photosynthesis may be about the maximum height for trees, and that is approaching the maximum height for trees. So interesting set of data here. We look at morphology, we see really extreme changes in morphology associated with height in these redwood trees. So these heights are in meters. So as they go up in height, what you can see is that this foliage becomes more and more constricted and essentially drought-like. These changes in morphology are what you would expect with changes in water availability. And we actually see that in this photo. Now, this is a really interesting photo. So what this is showing is foliage way up in the top of one of these redwoods. This is foliage attached to the tree right here. And you can see it has that really constricted, drought-like foliage. But this is also redwood foliage. This is from a little seedling that's rooted in a little mat of organic matter on a branch in that tree. So because that seedling is rooted and getting its water from that mat of organic matter, its water potential is not subjected to gravitational potential. It's getting water from right there. And its foliage morphology is like that foliage way further down in the tree. So these are seeing the same light environment, so light is not causing these differences. These differences in foliage morphology are just due to differences in water relations. So some really neat demonstrations of variation in morphology and physiology associated with height. So the great heights achieved by trees and the pulling of water to those great height. Those differences in water potential likely limits the major or the maximum height that can be achieved by trees. So really, that maximum height is limited by water relations, which is pretty cool.